Scientists have just issued another alert about Comet 3I Atlas. They are saying 3I Atlas. Just shifted again from its path, and we're witnessing something that defies our expectations at every turn. Just when the observations begin to crystallize, just when the mathematics start to align and we dare to say yes, now we understand what's happening, the cosmos delivers another surprise. It's like watching a shapeshifter move through space, refusing to be defined by our equations. For those following this extraordinary journey, you already know this is no ordinary visitor. This comet doesn't simply obey the laws we've written for such objects. It evolves, it transforms, it rewrites its narrative as it travels through our cosmic neighbourhood. And what we're seeing today represents perhaps the most compelling evidence yet that we're observing something genuinely anomalous unfolding before our eyes. Before we go further, consider subscribing and turning on notifications if this fascinates you. Switch to full screen and immerse yourself in what comes next. Let me share with you what's actually transpiring here. This latest alert transcends mere brightness anomalies or intriguing visual features in our imagery. Those details captivate us certainly, but what we're confronting now cuts to something far more fundamental. This time, the revelation emerged from the orbit itself. Think about what this means. Throughout the night, tracking stations distributed across our planet transmitted fresh, extraordinarily precise positional measurements. The same telescopes, the same observational protocols, the same data reduction algorithms they've always employed. Nothing in our methodology changed. Yet when these new coordinates were integrated into our orbital calculation systems, something unexpected occurred. The residuals began behaving strangely. Now residuals represent the tiny discrepancies between theoretical prediction and observed reality, where our mathematics tells us the comet should appear in the heavens versus where we actually find it. In an idealized universe with flawless calculations, these residuals would vanish to zero. But our universe isn't ideal, so small differences always exist. What matters is that these differences should remain random and minimal, scattered without pattern. That's not what happened. The residuals didn't merely increase slightly, they organized themselves, aligned in a coherent direction. This is profoundly significant because it reveals that something about the comet's fundamental motion has shifted. Consider this. With a typical asteroid or an extinct cometary nucleus, orbital prediction becomes remarkably precise using gravity alone. The Sun's gravitational embrace, the subtle tugs from distant planets, apply the mathematics and you know precisely where to find it. But 3I Atlas refuses to be typical. It's alive in the astronomical sense, constantly exhaling jets of gas and dust from its surface, into the void. And here's where Newton's elegant third law enters our story. When material erupts in one direction, the comet itself recoils in the opposite direction. We call this phenomenon a non-gravitational force, and it's rewriting the rules for this enigmatic traveller. Think of it as a cosmic engine constantly firing, perpetually nudging the comet away from the purely gravitational trajectory our equations predict. Until yesterday, we believed we had decoded this non-gravitational acceleration. We understood its direction, we had measured its strength, our orbital calculations incorporated these forces, and the universe appeared to make sense. But today, something extraordinary happened. To reconcile the new observations with reality, that push must now be oriented differently. The thrust vector from the comet's outgassing jets has rotated. Not dramatically perhaps, but sufficiently that our algorithms cannot dismiss it. The mathematics simply refuses to converge unless we accept that the comet's activity has fundamentally transformed. That revelation alone would capture the attention of any scientist. When a comet spontaneously alters its self-propulsion vector, we take notice. But here's where the story becomes truly remarkable. While the orbital dynamics team wrestled with these numerical anomalies, the imaging team independently completed their analysis of an entirely separate observational data set. They had meticulously combined multiple exposures from different observatories, constructing extraordinarily high-contrast images of the comet's inner regions. And because the cosmos has an elegant way of maintaining consistency, the visual evidence tells precisely the same story as the orbital mechanics. In last week's imagery, the inner coma and primary jet had appeared to stabilize into a predictable configuration. Any observer might have concluded, this is the current state. This is how the comet expresses itself. Today's images reveal a different reality. The inner coma, that luminous nebulous envelope surrounding the nucleus, has shifted its orientation. The brightest concentration of this glow has migrated. The primary jet, the most powerful stream of sublimating material, has tilted toward a new heading compared to its position just days ago. And the transformation extends beyond the dominant features. The secondary structures, those delicate fans and subsidiary streams, have rebalanced themselves in response. The entire architecture has reorganized. Even in the distant background, the comet's tail now exhibits a subtle serpentine curve absent from earlier observations. It's as though the entire structure experienced a gentle torsion. Now consider what we have. Two completely independent analytical approaches converging on an identical conclusion. The orbital calculations declare that the net force vector acting upon the comet has rotated. The direct imaging confirms that the physical jets and material streams erupting from the nucleus have rotated in concert. This isn't coincidence. This isn't some artifact of data processing. This is genuine physical evolution occurring on this object as we observe it. This is what NASA means when they announce that 3I Atlas has shifted once more. The comet is actively reconfiguring its outgassing behavior, which modifies its self-propulsion, which alters its trajectory through space. All of this unfolds in the present moment while humanity watches. The question that naturally emerges is why? What drives this restless transformation? To grasp the answer, we must first understand what a cometary nucleus truly is. It's not some monolithic stone hurtling through the void. It's something far more delicate and dynamic. A dirty snowball, if you will, or perhaps more accurately, a fragile conglomeration of frozen debris held together by the feeblest gravitational bonds imaginable. Its surface wears a dark armor, a crust of organic compounds transformed by cosmic radiation, across epochs spanning millions, perhaps billions of years. Yet beneath this protective shell lie reservoirs and strata of volatile ices. Water ice, carbon monoxide ice, carbon dioxide ice, all locked together with dust and mineral fragments in a delicate frozen matrix. As a comet approaches the Sun, this ancient ice begins to warm, but not uniformly. Solar radiation bathes only the hemisphere facing our star at any given instant. The insulating crust conducts thermal energy poorly, so heat percolates gradually into the deeper substrates. When temperatures climb sufficiently, those volatile ices undergo sublimation, transforming directly from solid to gas without passing through a liquid phase. Pressure accumulates beneath the crust until the structure can no longer contain it. A fissure opens. A weak region fails. Suddenly you have a jet, high-pressure gas laden with entrained dust particles erupting into the vacuum at hundreds of meters per second. Now here's what makes this fascinating. The surface of 3I Atlas likely resembles a complex mosaic of geological features, sealed fractures, dormant vents frozen over from earlier episodes of activity, volatile deposits at varying depths distributed chaotically across the nucleus, with no discernible pattern. For the past several months it appears one particular vent, or perhaps a cluster of vents, has dominated the activity. One major fracture has remained open, steadily expelling material, generating that prominent jet visible in our imaging. Because this source has maintained relative stability, the non-gravitational acceleration acting on the comet has likewise remained relatively constant. But this comet has spent months in space now, cycling through thermal extremes as it sweeps past the Sun and recedes outward again. The deep interior continues absorbing energy deposited during perihelion passage. Temperature gradients are evolving. Pressure accumulates in previously dormant regions. Fractures that were mechanically stable may now be approaching critical stress thresholds. Eventually something must yield. One scenario is straightforward. A new vent has breached the surface. Perhaps a reservoir of volatile ice lay buried beneath a fragile crustal layer on a different region of the nucleus. As thermal energy finally penetrated to that depth, the ice reached its sublimation threshold. Pressure escalated until it explosively ruptured the overlying material, and now you have an entirely new jet emanating from a completely different location. If this new source is sufficiently vigorous, if it expels enough gas and dust, it could compete with or even dominate the original vent. The instant that happens, the net thrust vector acting on the comet rotates, the trajectory shifts, and our images capture a transformed configuration. That's one explanation, and it's elegantly simple. New vent opens, activity pattern reorganizes, everything changes. But there's an alternative possibility that may be even more intriguing. Perhaps the entire nucleus is altering its rotation state. You see, when jets erupt from a comet, they don't merely push it along a single axis, they generate torque as well. Consider the physics of a rotating ice skater. Extend the arms outward, angular velocity decreases. Contract them inward, the spin accelerates. Complementary dynamics follow analogous laws, though instead of human limbs, we're dealing with gas jets erupting at chaotic angles from the nuclear surface. With every eruption, a subtle rotational force acts upon the body. Over countless revolutions, these seemingly negligible forces compound into measurable effects. Earlier data confirmed that 3I Atlas exhibits anything but straightforward rotation. There's no elegant spin around a singular unchanging axis here. The dynamics are considerably more elaborate. We're likely observing tumbling motion, or perhaps precession, following an intricate trajectory. Should the rotational axis be precessing, executing that characteristic wobble, reminiscent of a spinning top knocked off balance, then every vent's spatial alignment undergoes constant transformation. The vents themselves might remain fixed on the surface, their output steady. Yet the cosmic direction they face keeps evolving because the nucleus itself performs this gradual, perpetual wobble. If this describes our reality, then what we're seeing today, this latest directional shift in thrust, may simply be another frame in this slow-motion precessional evolution. Perhaps no new vents are awakening at all. Perhaps the existing ones are merely reoriented because the entire body has tilted through another degree of its wobble cycle. Both interpretations hold scientific merit. Both align with our measurements. In all likelihood, we're observing a hybrid phenomenon, fresh vents activating while rotation simultaneously transforms. We're dealing with a system of remarkable dynamical richness. Yet here's what troubles me as a physicist. With each thrust vector modification, with every newly active jet or axis reorientation, the internal stress architecture of this object undergoes radical reorganization. Reflect on what this means. The nucleus maintains only marginal structural coherence. There's no rigid skeleton here, no tensile strength to speak of. We're observing a gravitationally bound rubble pile, ice fragments and rocky debris clinging together through weak van der Waals forces and minimal gravitational attraction. When outgassing commences from a particular region, material gets ejected from that locale, redistributing mass and disrupting the delicate force equilibrium throughout the interior. Terrain that dwelled in perpetual shadow suddenly receives reflected solar radiation from neighboring features. Stress fractures that achieved stability under previous loading conditions now experience forces from entirely different vectors. Subsurface voids that had reached pressure equilibrium may now face compression or expansion beyond their previous experience. On short timescales, days, perhaps weeks, this appears as the phenomenon we're currently documenting. Another shift occurred. Jet alignment changed. Our trajectory models needed recalibration. Scientifically captivating, dynamically active, yet not immediately threatening. But extend the timeline to months, and these cascading stress redistributions accumulate consequences. Every reconfiguration adds another burden this delicate architecture must bear. Every fresh arrangement poses a structural endurance test. History offers us precedent here. Comets born within our solar system have followed this exact evolutionary pathway. We've documented the progression. Incremental non-gravitational force variations, morphing jet architectures, spin rates climbing as outgassing torques dominate. Then occasionally, with startling abruptness, total disintegration. The nucleus reaches its structural breaking point. Sometimes an object in space reaches a breaking point. The stresses build, the internal forces lose their balance, and then suddenly the nucleus can no longer hold itself together. When that happens, the comet can fracture into a few major chunks, or it can simply crumble into a diffuse swarm of debris and dust. In either case, the comet as a single unified body is gone. Now, to be absolutely clear, no one is officially claiming that 3I Atlas is on the verge of that fate. The wording in the official notices is careful and conservative. They speak of revised orbital solutions, measurable shifts in outgassing directions, changes in the net non-gravitational acceleration acting on the object. All rigorously technical, all deliberately neutral. But consider the subtext. You do not allocate precious telescope time. You do not ask observatories to increase cadence and tighten their coverage. You do not circulate internal notices to multiple research teams if you believe you are witnessing something mundane. You do that because something genuinely interesting is underway, something that might evolve into a much more dramatic story. You do it because this object is active in a way that matters, in a way that could carry real consequences for its future. So what does this all add up to? It means that 3i Atlas is not quietly drifting out of the solar system along some frozen, unchanging path. Its story is not over. It is still venting, still erupting, still sculpting its own trajectory layer by layer, jet by jet, rotation by rotation. Yesterday the thrust direction shifted. Today it's shifted again. If that keeps happening, if each new orbital fit demands a new thrust vector, if each new image shows the jets leaning a bit further, then we're effectively watching a physics experiment play out in real time. What makes this so profound is that 3i Atlas is not native to our cosmic neighbourhood. This comet was born around some distant star in a planetary system utterly separate from our own, perhaps billions of years ago. It has spent eons wandering through the frigid emptiness between the stars, locked in darkness, frozen and inert, slowly tumbling through interstellar night. Then, by sheer chance, its trajectory intersected our solar system. It fell toward our sun, warmed for the first time in an unimaginably long interval, and awakened. It began to do what comets do, outgassing, forming jets, growing a coma and a tail. But it is doing all of this with a composition and internal structure forged under alien conditions, unlike the comets we know so well from our own system. That is the central mystery. We do not yet know how dense this object is, how strong its internal framework might be, how volatile its ices are, or how its interior layers are arranged. We are inferring all of that by watching how it reacts to sunlight, to heating, to its own outgassing. And what the behaviour tells us so far is that this comet is restless. It is unstable. It refuses to settle into a simple pattern. Perhaps, given enough time, the activity will calm. Perhaps in a few weeks or months the jets will diminish, the configuration will stabilise, and 3i Atlas will limp away, mostly intact, fading gradually as it escapes back into the deep interstellar dark. Or perhaps the stresses will continue to mount. Perhaps one more jet will open, or one more subtle change in the spin will redistribute the load just slightly beyond what this fragile structure can bear, and then something fundamental will fail. Right now, no one can say which path it will take. That uncertainty is what makes this object both exhilarating and exasperating to study. We are watching an interstellar visitor experience its first and possibly only close pass by our sun, and the ending to this cosmic story has not yet been written. This latest alert is not an ending but another chapter in an unfolding cosmic drama. It is a reminder that 3i Atlas is not the kind of object you observe once, file away, and forget. Each time we turn our instruments toward it, the story has shifted. Each update answers one question and asks two more. Will the next bulletin tell us that 3i Atlas has finally settled into a stable, quiet state? Or will it reveal yet another change, perhaps more dramatic than any we have seen so far? The universe is not telling us in advance. The only way to know is to keep watching. And that is precisely what is happening right now. Across the planet, observatories are tracking this fugitive from another star system. On every clear night somewhere, someone is measuring its position, its brightness, its structure. The orbit solutions grow more precise. The images gain clarity. The theoretical models are revised and refined. Slowly, piece by piece, a picture emerges from the noise. This is why comets are so captivating. They are not rigid clockwork mechanisms. They are fragile, volatile, evolving worlds capable of surprising us from one night to the next. When that comet is not merely from the outer reaches of our own system, but from the deep interstellar gulf, when it may be the only specimen of its kind humanity will ever see, every subtle change becomes precious. Each rotation of a jet, each small adjustment in the thrust vector, each orbital tweak becomes a clue to how comets form and live in distant planetary systems scattered throughout the galaxy. So yes, 3i Atlas has shifted again. The jets have rotated, the orbit has been nudged, the invisible hand of its own outgassing has tilted its path once more. It is one more step in an evolution we do not yet fully grasp. Whatever comes next, whether it is a gentle settling into stability or a more violent transformative event, we will be there, watching, measuring, learning. Because with an interstellar visitor like this, no change is truly small. Any tiny adjustment in its behavior may carry within it a profound revelation about how nature builds, stresses, and sometimes destroys these icy messengers between the stars. But here's what the data is revealing now, something that goes beyond simple trajectory adjustments and enters territory that makes veteran astronomers pause and reconsider everything they thought they understood about cometary mechanics. The non-gravitational acceleration isn't just changing direction, it's changing magnitude. And that difference, that shift in the actual strength of the force pushing this comet around, tells us something deeply significant about what's happening inside the nucleus itself. Let me explain why this matters so much. When we first started tracking 3I Atlas's non-gravitational forces, we measured them at a certain level. Let's call it baseline thrust. The comet was producing jets. Those jets were pushing it in a specific direction, and we could quantify that push with remarkable precision. Over weeks and months, that measurement remained relatively stable. Sure, there were fluctuations, small variations, that we attributed to the comet's rotation bringing different active regions into and out of sunlight. But the overall magnitude, the total amount of thrust being generated, stayed within predictable bounds. Not anymore. The latest data shows that the total force has increased, not by a small margin that could be explained by measurement uncertainty or observational noise, by a statistically significant amount that demands explanation. The comet is now pushing itself harder than it was a month ago. And when you dig into what that means physically, when you think about what has to happen inside a cometary nucleus to produce more thrust, you realize we're watching something genuinely extraordinary unfold. Thrust from outgassing depends on several factors. How much volatile material is sublimating per unit time? How fast that gas is escaping into space? How much dust is entrained in the gas flow? And critically, how much of the nucleus surface is actively venting? If the total thrust is increasing, then at least one of those factors must be changing. Either the existing vents are becoming more active, expelling material at higher rates, or new vents are opening, adding their contribution to the total output, or both processes are occurring simultaneously. The first possibility suggests that heat is penetrating deeper into the nucleus, reaching ice reservoirs that were previously too cold to sublimate. As 3I Atlas continues its journey, even though it's now moving away from the Sun, thermal energy deposited during its close approach continues diffusing inward. Cometary nuclei are excellent insulators. Heat doesn't move through them quickly. It can take weeks or months for the warmth from perihelion to reach the interior layers. When it finally does, when that thermal wave arrives at depths where substantial volatile ices reside, sublimation rates can surge dramatically. The second possibility is perhaps more concerning from a structural stability standpoint. New vents opening means new fractures forming, new weak points in the crust failing, new pathways for gas to escape. Each new vent represents a location where the internal pressure exceeded the mechanical strength of the overlying material. And here's the troubling part. Once a vent opens, once that pathway is established, it rarely closes. The escaping gas erodes the vent walls, widening the aperture, making it easier for more material to escape. It's a positive feedback loop. More venting leads to more erosion, leads to larger vents, leads to more venting. What we're potentially witnessing is the early stage of a runaway process. Not immediate catastrophic disintegration, but the gradual acceleration toward it. Think of it like cracks spreading through ice. At first, they're small, isolated, manageable. But as more cracks form, as they begin to interconnect, the structural integrity of the entire sheet degrades. Eventually you reach a point where one more crack, one more stress, causes the whole thing to shatter. The mathematics of fracture mechanics is brutally clear on this. There's a threshold beyond which recovery becomes impossible. Now, let me be careful here. We're not saying 3I Atlas has crossed that threshold. We're not predicting imminent breakup. What we're saying is that the trends we're observing, the increasing thrust magnitude combined with the changing thrust direction, are consistent with a nucleus undergoing progressive destabilization. It's like watching a building develop cracks. You can't predict exactly when or if it will collapse, but you can recognize that the structural situation is degrading, not improving. And that recognition changes how we approach observation and analysis. This is why NASA and other space agencies have quietly ramped up their monitoring cadence. This is why telescope time that was scheduled for other projects is being redirected toward 3I Atlas. This is why the tone of the internal communications, while professionally neutral, carries an undercurrent of heightened attention. Because if this comet is going to do something dramatic, if it's going to fragment or undergo a major outburst, or exhibit some other form of extreme activity, we want to be watching when it happens. These events are rare, they're scientifically invaluable, and they happen on timescales that don't wait for proposal cycles or scheduling committees. You have to be ready to observe when nature decides to put on a show. But there's another layer to this story that hasn't received much attention in the public discussions, though it's absolutely central to how researchers are thinking about 3I Atlas. The composition question. This comet came from another star system. It formed in a protoplanetary disk with a chemical makeup potentially very different from our own solar system's disk. The ratios of different ices, the abundance of organics, the mixture of rocky and volatile materials, all of these could be substantially different from what we see in native solar system comets, and those differences matter enormously when trying to predict behavior. Solar system comets, the ones we've studied extensively, have taught us certain rules. Water ice sublimates at certain temperatures. Carbon dioxide ice is more volatile, sublimating at lower temperatures. Carbon monoxide ice is even more volatile. Methane ice, ammonia ice, each has its own sublimation curve, its own temperature threshold. We use these known properties to model how comets should behave as they approach and recede from the Sun. We predict which ices will become active at which distances, how the activity should evolve over time, what the coma composition should look like. But what if 3I Atlas doesn't follow those rules? What if its formation in an alien stellar system gave it a composition that doesn't match our templates? Spectroscopic observations have provided some clues. The coma shows water, as expected. It shows carbon-bearing molecules, also expected. But the ratios are slightly off from typical solar system comets. Not wildly different, not so alien that we can't recognize what we're seeing, but different enough that it raises questions. Is the nucleus richer in certain volatiles than we're accustomed to? Does it have ices we haven't detected yet, exotic species that don't show up prominently in our spectra, but might be driving unexpected behavior? This uncertainty propagates through every aspect of our analysis. When we try to model the internal structure, we have to make assumptions about density, porosity, ice-to-rock ratio. When we try to predict outgassing rates, we have to assume certain compositions and sublimation properties. When we try to understand the non-gravitational forces, we have to estimate how efficiently the jets convert sublimation into thrust. All of these calculations rest on a foundation of assumptions that might not apply to an interstellar visitor. And when the object starts behaving in ways that don't quite match our predictions, we're left wondering whether we're seeing genuinely anomalous activity or whether our models are simply inadequate for this particular object. That ambiguity is maddening for scientists who crave clear answers, but it's also part of what makes 3I Atlas so scientifically valuable. Every deviation from expected behavior, every surprise, every shift that forces us to revise our models teaches us something about the diversity of cometary bodies in the galaxy. It tells us that planet formation around other stars doesn't produce carbon copies of our solar system. It creates variations, objects with their own unique properties shaped by their local conditions. And studying those variations expands our understanding of what's possible, what's common, what's rare in the cosmic inventory of small bodies. So when NASA announces another shift in 3I Atlas's trajectory, when the orbital calculations have to be redone yet again, when the images show yet another reorganization of the jet structure, it's not just an update on one interesting comet. It's another data point in our ongoing education about how the universe makes these objects, how they evolve, how they respond to solar heating, how they ultimately meet their end. Each shift, each change, each unexpected behavior is a lesson. And we're learning fast because this comet is teaching us constantly, day by day, week by week, refusing to settle into predictable patterns, refusing to let us get comfortable with our understanding. That's the real story here. Not just that 3I Atlas has shifted again, though that's fascinating in itself, but that it keeps shifting, that it's dynamically active in ways that challenge our models, that it's revealing itself to be more complex than the simple, dirty snowball picture suggests. This is an object with internal structure we don't fully understand, with composition we're still trying to decode, with behavior that refuses to be neatly categorized. And as it continues its journey through our solar system, as we continue watching it evolve, every new observation has the potential to reveal something unexpected. The current shift might be just another in a series of minor adjustments, or it might be the beginning of something more significant. The only way to know is to keep watching, keep measuring, keep analysing, and that's exactly what the astronomical community is doing, with increasing intensity, with growing fascination, with the recognition that opportunities like this don't come along often. We have an interstellar visitor actively changing before our eyes, and we're privileged to witness it. Whatever comes next in this story, whether it's gradual stabilization or dramatic transformation, we'll be there to document it, to study it, to learn from it. Because that's what we do. We watch the universe, we measure what we see, and we try to understand what it all means. And what it means right now is that we're witnessing something the textbooks didn't prepare us for. The data is telling us something, but the message isn't entirely clear yet. Is this comet following a path toward eventual stability, or are we watching the early stages of something more dramatic? To answer that question, we need to look at what's happened to other comets that have exhibited similar behavior patterns. And when we do that comparison, when we examine the historical record, the picture that emerges is both fascinating and somewhat unsettling. Let's start with the comets we know best, the ones from our own solar system that have given us decades or even centuries of observational data. Comet Halley, perhaps the most famous periodic comet, has been tracked through multiple apparitions, and what we've learned is that each time it returns, each time it swings around the Sun and undergoes another heating cycle, it changes slightly. The jets shift position, the outgassing rates evolve, the non-gravitational forces acting on it modify its orbit in subtle but measurable ways. Over centuries, these small changes accumulate. The comet's period lengthens or shortens by a few days. Its perihelion distance shifts by small amounts. What makes Halley particularly instructive is that we've watched it long enough to see patterns emerge. The changes aren't random. They follow a certain logic driven by the comet's rotation state, by the distribution of volatile ices across its surface, by the evolution of its active regions over time. Scientists have built sophisticated models that can explain most of Halley's behavior, models that successfully predict where the jets will be active during each apparition, how the orbit will change, how the comet will respond to solar heating. Those models work because we have enough data, enough observations spanning enough time, to constrain the parameters accurately. We don't have that luxury with 3I Atlas. This is its first and likely only passage through our solar system. We don't know what it was like before it arrived. We don't know how many previous perihelion passages it might have experienced around its parent star before being ejected into interstellar space. We're seeing a snapshot, a single frame from a much longer movie, and we're trying to understand the entire plot from that one image. That's extraordinarily difficult. It's like trying to diagnose a patient's condition from a single medical test, without any history, without knowing what's normal for that individual, without understanding their baseline. But we can look at other comets that have shown similar characteristics during their own first observed passages. Comets that exhibited strong variable non-gravitational forces, comets whose jet structures reorganized dramatically over short periods, comets that seemed restless, unstable, reluctant to settle into predictable patterns. And when we examine those cases, we find a spectrum of outcomes. Some eventually stabilized. The activity calmed, the jets found a quasi-steady configuration, and the comet continued on its way without incident. Others did not stabilize. The activity intensified, new vents continued opening, structural stresses mounted, and ultimately the nucleus fractured. Comet Schwarzmann-Wachmann 3 is a particularly relevant example. This periodic comet was observed to fragment dramatically during its 1995 apparition, breaking into multiple pieces that continued orbiting the Sun on slightly different trajectories. But here's the critical detail. The fragmentation wasn't sudden or unpredictable. It was preceded by months of increasingly erratic behavior. The brightness varied wildly. Outburst events became more frequent. The coma structure reorganized repeatedly. All the signs were there that something fundamental was happening to the nucleus structure. And then, when the stresses finally exceeded the critical threshold, the breakup occurred. The fragmentation of Schwarzmann-Wachmann 3 was extensively studied because it happened during an era when we had good telescopes and could track the pieces as they separated. What researchers learned was that the fragmentation process itself was complex and extended. The nucleus didn't just explode into a cloud of debris, It split into several major fragments, each tens to hundreds of meters across, which then continued to fragment further over subsequent weeks and months. Some fragments survived and remain observable today, essentially becoming separate comets following nearly identical orbits. Others disintegrated completely, crumbling into dust that spread out along the orbital path. What drove that fragmentation? The prevailing theory is that it was a thermal stress failure. As the comet approached perihelion, solar heating created temperature gradients within the nucleus. Different materials expand at different rates when heated. Ice sublimates and creates pressure. The structural bonds holding the nucleus together, already weak due to the porous, loosely consolidated nature of cometary nuclei, couldn't handle the stress. Cracks formed and propagated, and eventually the nucleus reached a point where it could no longer maintain its structural integrity. It came apart. Now, I want to be absolutely clear about something. I am not predicting that 3I Atlas will fragment. The current data does not support that conclusion. What I am saying is that the behavioral patterns we're observing, the repeated shifts in jet configuration, the increasing thrust magnitude, the restless evolution of activity, these are the same types of signatures that preceded fragmentation events in other comets. That doesn't mean fragmentation is inevitable or even likely. It means we need to pay attention. It means this comet deserves close, continuous monitoring because its behavior suggests internal stresses and ongoing evolution that could lead anywhere. The fragmentation question is particularly interesting for an interstellar comet because we don't know how these objects compare structurally to solar system comets. Are they stronger or weaker? Are they more tightly bound or more loosely aggregated? The environment where they form, the conditions in another stellar system's protoplanetary disk, might produce nuclei with very different properties than the comets born in our own system. Perhaps interstellar comets are more robust, able to withstand stresses that would shatter a solar system comet. Or perhaps they're more fragile, having spent eons in interstellar space, experiencing thermal cycling and cosmic ray bombardment that weakened their structure. The cosmic ray question is actually quite important and often overlooked. When a comet is orbiting within a stellar system, it's somewhat protected by that star's heliosphere, the bubble of solar wind that deflects galactic cosmic rays. But in interstellar space, there's no such protection. Cosmic rays, high-energy particles accelerating through the galaxy, bombard the comet's surface and penetrate into its interior. Over millions of years, this bombardment can alter the chemical and physical properties of the ice. It can break molecular bonds, create new compounds through radiation chemistry, and potentially weaken the structural integrity of the material. We have very limited understanding of how extensive this cosmic ray processing is, or what effects it has on cometary nuclei. Laboratory experiments can simulate some aspects, exposing ice samples to high-energy radiation and measuring how their properties change. But those experiments are necessarily limited in duration and scale. You can't really replicate millions of years of cosmic ray exposure in a lab. So we're left with theoretical models and indirect observations, neither of which provide complete certainty about what we should expect from an interstellar comet structure. This uncertainty compounds when we try to predict 3I Atlas's behavior. We don't know if its time in interstellar space made it stronger or weaker. We don't know if radiation processing created a more cohesive crust or a more friable one. We don't know if the interior is pristine, unchanged since formation, or altered by radiation penetrating from the surface. These unknowns make it difficult to predict with confidence whether the nucleus can withstand the current stresses or whether we're approaching a fragmentation threshold. We simply don't have enough examples to know. Oumuamua, the first confirmed interstellar visitor, didn't show significant cometary activity. No coma, no tail, no jets. Either it was an asteroid, essentially an inert rocky body, or it was a comet with such minimal activity that we couldn't detect it. Either way, it didn't provide useful information about how active interstellar comets behave. 2I Borisov, the second interstellar visitor, did show cometary activity and behaved fairly normally by solar system standards. It had a coma, it had a tail, it underwent outgassing that modified its trajectory slightly. But it didn't exhibit the kind of dramatic repeated shifts we're seeing with 3I Atlas. It was in many ways disappointingly ordinary. That makes 3I Atlas unique among the 3 confirmed interstellar objects we've detected. It's the only one showing this level of dynamical complexity, this degree of ongoing evolution. And that uniqueness makes it both scientifically invaluable and interpretatively challenging. We can't assume it's representative of interstellar comets in general. It might be an outlier, an unusual specimen that happens to be particularly active or structurally unstable. Or it might be perfectly normal for its population, and Borisov was the outlier, an unusually stable interstellar comet that gave us a false impression of what to expect from these objects. This raises interesting statistical questions about the population of interstellar comets. If we had a large sample, hundreds or thousands of these objects, we could start to answer questions about what's typical, what fraction shows strong activity, what fraction fragment, what's the distribution of compositions, sizes, activity levels. But with a sample size of 3, 2 of which aren't very informative for understanding active behavior, we're essentially flying blind. It's like trying to understand human biology by examining 3 people, one of whom is asleep, one of whom is sitting quietly, and one of whom is running a marathon. The marathon runner might be completely normal, or they might be exceptional. You can't tell from such a limited sample. This statistical limitation frustrates researchers because it means every conclusion has to be heavily caveated. Based on the limited sample available, given the uncertainty in population characteristics, assuming 3i Atlas is representative, which may not be valid. These qualifiers are necessary for intellectual honesty, but they make it difficult to draw strong conclusions or make confident predictions, and that ambiguity, that uncertainty, permeates every discussion about what we should expect next from this comet. The uncertainty extends beyond just the interstellar comet population to comets in general. Despite decades of observations and multiple spacecraft missions to comets, we still don't have a complete understanding of cometary physics. Every new comet studied reveals surprises, behaviors that don't quite fit existing models, observations that require theoretical explanations to be revised or extended. Comets are complex objects operating in extreme environments. They're subject to intense solar radiation, vacuum conditions, temperature extremes ranging from near absolute zero in deep space to well above the freezing point of water at perihelion. They contain multiple components, ices, organics, minerals, all interacting in complicated ways as conditions change. Building accurate models of cometary behavior requires incorporating all these factors and more. You need to understand radiative transfer, how sunlight penetrates into the nucleus and deposits heat at various depths. You need to understand thermodynamics, how that heat drives phase transitions and creates pressure gradients. You need to understand fluid dynamics, how gas flows through porous media and escapes into vacuum. You need to understand structural mechanics, how stresses accumulate and how materials fail under those stresses, and you need to understand all these processes as they occur simultaneously and interact with each other in nonlinear ways. The computational models that attempt to capture all this complexity are sophisticated and impressive. They divide the nucleus into thousands or millions of computational cells, track temperature, pressure, composition, and stress in each cell, and evolve the system forward in time according to the governing equations. But even the best models require simplifications and assumptions. You can't track every molecule, every grain of dust, every microscopic crack. You have to parameterize small-scale processes, represent them with effective equations that capture their average behavior, and those parameterizations introduce uncertainty that propagates through the calculation. For a solar system comet with extensive observational data, you can tune the model parameters to match observations, effectively calibrating the model to that particular object. But for 3i Atlas, where we have limited data and no previous observations to calibrate against, the models are necessarily more uncertain. Different reasonable choices for parameters can produce different predictions for how the comet should behave, and when the observed behavior doesn't match any of the predictions, you're left wondering whether your parameters were wrong, your physics was incomplete, or the comet is doing something genuinely unexpected that requires new theoretical understanding. This is the situation researchers face with 3i Atlas. The observations are clear. The comet is shifting, evolving, changing in ways that demand explanation. But the explanations are uncertain because we don't have enough constraints on the system. Multiple scenarios could produce similar observational signatures. And distinguishing between them requires additional data, more observations, longer time baselines. In the meantime, researchers do their best to bracket the possibilities, to identify what scenarios are most consistent with available data, to make provisional interpretations while acknowledging the uncertainties involved. That intellectual humility, that willingness to say, we don't know for certain, is a strength of scientific thinking, not a weakness. It reflects an honest assessment of evidential limitations rather than overconfident speculation presented as fact. But it can be frustrating for people who want definitive answers. Will it fragment or won't it? Is it unusual or typical? What will happen next? The honest answer to all these questions is we're not certain yet. And while that honesty is admirable, it doesn't satisfy the human desire for clear narratives and definite predictions. This uncertainty permeates every discussion among the research teams actively studying 3I Atlas. In the conference calls, in the email exchanges, in the collaborative analysis sessions, you hear the same questions repeated. Is this normal? Is this what we should expect from interstellar comets? Or is this something special, something unusual that we need to understand on its own terms rather than by comparison to solar system examples? The honest answer is that we don't know yet. We need more data. We need to see how this story resolves, and we need to find more interstellar comets to study so we can build a statistical understanding of their properties. That last point is particularly important and worth dwelling on. Right now, we're working with a sample size of 3, and 2 of those 3 aren't very helpful for understanding active cometary behavior. One didn't show activity at all, one showed minimal activity, and one 3I Atlas is showing extraordinary activity. You can't draw general conclusions from a sample that's skewed. It's not just that the sample is small, it's that the sample is potentially biased in ways we can't assess, because we don't know the underlying population distribution. Think about it this way. If we detected 10 interstellar comets and 7 of them showed strong variable activity like 3I Atlas, we'd conclude that such behavior is typical, common, perhaps even the norm. If we detected 10 interstellar comets and only 1 showed strong activity, we'd conclude that 3I Atlas is unusual, an outlier, not representative. But with only 3 detections, we can't make either conclusion confidently. The true population characteristics remain hidden behind the statistical noise of small numbers. This is why the astronomical community is so eager for better detection capabilities. The Vera Rubin Observatory, currently under construction in Chile, will revolutionize our ability to find these objects. Its wide-field survey camera will scan the entire visible sky every few nights with unprecedented sensitivity. Current estimates suggest it might detect dozens of interstellar objects per year once fully operational. That would transform our understanding from the current situation, where we're desperately trying to learn everything we can from the few examples we've found, to a future where we have enough specimens to start recognizing patterns, to classify different types, to understand what's typical versus what's anomalous. The Rubin Observatory is scheduled to begin full survey operations in late 2025, though that timeline has experienced delays and might slip further. When it does come online, it will image approximately 18,000 square degrees of sky, essentially the entire visible sky from its location in Chile, every few nights. Each image will be compared to previous images of the same sky region, automatically identifying anything that has moved, changed, or appeared where nothing was before. This includes asteroids, comets, variable stars, transient phenomena like supernovae, and crucially, interstellar objects passing through the solar system. The detection algorithms will flag objects moving on trajectories inconsistent with solar system orbits. Those objects will be prioritized for follow-up observations to determine if they're genuinely interstellar or just solar system objects on unusual orbits. The rapid cadence of the survey, revisiting each sky patch every few nights, means that we'll catch interstellar visitors early in their passage through the solar system, when they're still relatively bright and amenable to detailed study. No more discovering objects weeks or months after they've passed their closest approach, when they're already fading and heading back into the outer solar system. With that improved detection capability, the sample of known interstellar objects will grow rapidly. Within a decade of Rubin's full operation, we might have catalogued hundreds of interstellar visitors. That statistical sample will enable robust analysis of population characteristics. We'll be able to answer questions like, what fraction are asteroids versus comets? What's the typical size distribution? How common is strong outgassing activity? Are there compositional differences between objects from different regions of the galaxy? Do younger interstellar objects behave differently than older ones? All these questions are currently unanswerable with our sample of 3, but they'll become tractable once we have hundreds of examples to study. That future is tantalizingly close, but not quite here yet. For now, we have 3I Atlas, and 3i Atlas is demanding our attention with its continued evolution, its refusal to settle into a stable state, its ongoing surprises. The latest shift, the one that prompted NASA's recent alert, is significant not just because it happened, but because it continues a pattern. This isn't a one-time adjustment followed by stability. This is repeated, ongoing change, and that pattern suggests we're not seeing transient responses to changing solar conditions. We're seeing something more fundamental about how this particular nucleus is put together and how it's responding to the entire experience of solar heating. Let me paint a more detailed picture of what might be happening inside this object, based on the data we have and the models we're developing. Imagine the nucleus, roughly a few kilometers across, an irregular potato-shaped mass of ice and rock. The surface is dark, covered in that organic-rich crust built up over billions of years. But that crust isn't uniform. It has thin spots and thick spots, weak points and strong points, variations that reflect the heterogeneous nature of the original material that accreted to form the comet. Beneath it, the ice isn't distributed evenly. There are layers and pockets and regions of varying composition. Some areas are rich in water ice, others in more volatile species like carbon monoxide or carbon dioxide. The internal structure might be layered, like an onion, with different composition at different depths reflecting conditions at different stages of the protoplanetary disk's evolution. Or it might be more chaotic, with different materials mixed in irregular patterns, reflecting the turbulent accretion process that assembled the nucleus. We don't know which model is more accurate because we've never seen inside a cometary nucleus. All our knowledge comes from surface observations and theoretical modelling. As solar heating penetrates this complex structure, different regions reach their sublimation thresholds at different times. Initially, the most volatile ices in the shallowest, most sun-exposed locations begin sublimating. These create the first jets, the initial outgassing that we detected months ago. But as more thermal energy soaks deeper into the nucleus, as the heat works its way into the interior through slow conduction, new regions reach critical temperatures. Pockets of volatile ice that were too cold to sublimate suddenly cross the threshold. Pressure builds beneath crust that was previously stable, and eventually, a new vent opens. Each new vent changes the force balance acting on the nucleus. The thrust vector rotates because you now have jets pointing in different directions. The total magnitude increases because you have more total gas production from more active vents. And critically, the opening of a new vent often triggers changes in nearby regions. The sudden release of pressure can cause adjacent material to shift, can open pathways for heat to penetrate more quickly, can destabilize neighboring areas that were marginally stable before. It's a cascading effect. One change triggers others, which trigger still more changes. The system doesn't equilibrate quickly. It continues evolving. Now add the rotational dynamics. As new jets open, as the thrust pattern changes, torques are applied to the nucleus that alter its spin state. The rotation axis might precess, that characteristic wobble like a spinning top that's been knocked off balance. The spin rate might change, accelerating or decelerating depending on where the jets are located and which direction they point. And those rotational changes in turn affect which regions of the surface receive peak solar heating at any given time. A vent that was moderately active when it was rotating through sunlight for only a few hours per day might become hyperactive if the rotation changes such that it spends more time in direct sun. Or conversely, a previously dominant vent might become less active if rotational evolution moves it into a less favourable orientation, spending more time in shadow. These feedback loops make predictive modelling extraordinarily difficult. You can't simply say, at this distance from the sun, these ices will sublimate, producing this much thrust. You have to account for the changing surface orientation, the evolution of vent locations, the modification of rotation state, the cascading structural effects of ongoing activity. The system is dynamically coupled in complex ways. Small changes propagate through the entire model, affecting everything through these nonlinear couplings. And when your baseline understanding of the object's interior structure is uncertain because it's an interstellar visitor with unknown composition, when you don't know the mechanical properties of the materials, when you don't know how the ice and rock are arranged, the uncertainties compound rapidly. Different assumptions about internal structure lead to different predictions about behavior. And when behavior doesn't match predictions, you're left wondering which assumptions were wrong. This is why the research teams analysing 3i Atlas are being cautious in their predictions. They're presenting the observations, describing what they see, discussing possible mechanisms, but they're not making bold claims about what will happen next. Because honestly, they don't know. The system is too complex, too poorly constrained, too novel for confident forward prediction. What they can say is that the comet is active, evolving, and bearing close watching. That's the responsible scientific position when faced with a phenomenon you don't fully understand yet. But here's something that isn't uncertain. The scientific value of what we're observing is immense. Every shift in 3I Atlas's behavior, every reorganization of its jet structure, every adjustment to its trajectory provides data that feeds into our models of cometary physics. We're learning how heat propagates through these objects under conditions we've never observed before. We're learning how sublimation couples to structure and dynamics in a nucleus with potentially different composition than solar system comets. We're learning about the diversity of cometary behaviors possible in the galaxy. All of this knowledge, accumulated observation by observation, measurement by measurement, is advancing our understanding of these enigmatic bodies. And the implications extend beyond just comets. Understanding how volatile rich bodies respond to thermal stress, how their internal structure affects their evolution, how they ultimately meet their end, this knowledge is relevant to broader questions in planetary science. How did the early solar system evolve? What role did cometary impacts play in delivering water and organics to Earth? How do planetary systems in general dispose of their primordial debris? What happens to material ejected from one system that eventually gets captured by another? These large questions all connect to the detailed physics of how individual comets behave. And 3I Atlas is teaching us that physics in unprecedented detail, revealing behavior that challenges and refines our theoretical understanding. There's also a human dimension to this story that's worth acknowledging. Scattered around the planet at observatories and research institutions are teams of dedicated scientists who have reoriented their work to focus on this object. Telescope time that was scheduled for other projects has been reassigned. Graduate students have shifted their thesis research to incorporate 3I Atlas data. Postdocs are staying up through the night running new orbital integrations every time fresh observations arrive. Senior scientists are setting aside papers they were working on to focus on this unexpected visitor. That kind of collective effort doesn't happen often in astronomy. Most of the time, research proceeds at a measured pace. You propose observations months or years in advance. You collect data systematically. You analyze it carefully. You publish results that advance understanding incrementally. But occasionally something happens that demands immediate attention, that justifies disrupting normal schedules and redirecting resources. A supernova in a nearby galaxy, a gravitational wave detection, an asteroid on a close approach trajectory, and now an interstellar comet that won't stop evolving. The scientists involved aren't doing this for fame or recognition. Most of them will remain anonymous to the public. Their names might appear on technical papers read by a few hundred specialists. What drives them is the same thing that drives all fundamental research: curiosity, the desire to understand, the recognition that they're witnessing something genuinely interesting and possibly unique. They're living through a moment that will be written about in astronomy textbooks decades from now. Students in 2050 or 2075 will read about 3I Atlas as one of the early interstellar comets that taught us how these objects behave, and they're determined to document it as thoroughly, as accurately, as completely as possible. Because here's the thing about transient phenomena in astronomy. You can't go back and get more data if you miss the moment. If 3I Atlas fragments next week and we're not watching closely, we lose that information forever. If it does something unexpected and we don't have instruments pointed at it when it happens, we'll never know exactly what occurred. The universe doesn't replay events for our convenience. You get one chance to observe, one opportunity to measure, and if you miss it, it's gone. That pressure, that awareness of the fleeting nature of the opportunity, focuses attention like nothing else. So when NASA issues an alert saying 3I Atlas has shifted again, it's not just a bureaucratic update, it's a call to action. It's saying to the astronomical community, this object is still doing interesting things, stay alert, keep observing, don't look away, and the community responds. Telescopes are retasked, observation schedules are adjusted, people clear their calendars to analyze the incoming data, because everyone understands that this might be their only chance to study an actively evolving interstellar comet up close. The next one might not arrive for years. might not be as well positioned for observation, might not be as active or interesting. You work with what the universe gives you. Now let's talk about what happens next from an observational standpoint. The current monitoring campaign is intensive but sustainable. Multiple observatories are checking on 3i Atlas regularly, perhaps every few nights when weather and scheduling permit. They're taking images to track the coma morphology, spectra to monitor the composition, astrometric measurements to refine the orbit. This cadence is sufficient to catch major changes but might miss rapid transient events. If the comet undergoes a sudden outburst, if a large fragment breaks away, if something dramatic happens on a timescale of hours rather than days, we might not catch it in real time. That's the trade-off between coverage and resources. You can't keep every telescope pointed at one object continuously. There are other things to observe, other science to pursue, operational constraints and weather limitations. But if the behaviour continues escalating, if the shifts become more frequent or more dramatic, the decision might be made to increase monitoring intensity. That would mean more frequent observations, possibly continuous coverage using a network of telescopes distributed in longitude so that at least one always has the comet in a dark sky. That level of attention is expensive in terms of telescope time and human resources. It's only justified if you believe something significant might occur, and that's the question the community is grappling with now. Has 3i Atlas's behaviour escalated to the point where continuous monitoring is warranted, or are we still in a regime where the regular monitoring cadence is sufficient? Different researchers have different opinions on this, based partly on their interpretation of the data and partly on their tolerance for risk. Conservative scientists say the current approach is fine, we're not missing anything critical. More aggressive scientists argue we should increase coverage now before something happens that we fail to catch. There's no right answer to that debate. It's a judgment call balancing scientific opportunity against practical limitations. But what's not debatable is that 3i Atlas has earned special attention. It's not being treated like a routine object anymore. It's graduated to the category of targets that justify flexible, responsive observation strategies. And that status reflects the collective assessment of the community that this comet is genuinely unusual, genuinely interesting, and genuinely worth the extra effort required to study it properly while we still can, before it fades from view and the opportunity is lost forever, leaving us with whatever data we managed to collect and a lifetime of wondering what we might have learned if only we'd observed more closely, more frequently, more carefully during the brief window when this messenger from another star was close enough to study in detail. And understanding what makes it tick is precisely what drives the teams working on this object day and night. Because beneath all the technical details, beneath the orbital residuals and thrust vectors and spectroscopic measurements, there's a deeper question that haunts everyone involved with this research. What is the fate of 3i Atlas? Not just in the immediate sense of whether it will fragment or stabilize, but in the cosmic sense of what happens to objects like this over the vast stretches of time and space they traverse. This comet has already lived an extraordinary life, and we're witnessing what might be its final act. Think about the journey this object has taken. It formed billions of years ago in a protoplanetary disk around some distant star, a star we may never identify, in a stellar system we'll never observe directly. It coalesced from the debris of that disk, accumulating ice and rock and organic compounds in the cold outer regions far from its parent star. For perhaps millions or even billions of years, it orbited in that system, a frozen remnant of planet formation, slowly circling in the darkness while planets formed closer in, while the system evolved and matured and settled into its final configuration. Then something happened. Perhaps a planet migrated, its gravitational influence sweeping through the region where 3i Atlas orbited. Perhaps a passing star perturbed the system, its gravity reaching across light years to nudge objects in the outer reaches onto new trajectories. Perhaps there was a close encounter with a massive planet, a gravitational slingshot that accelerated this comet to escape velocity. Whatever the mechanism, 3i Atlas was ejected from its home system, flung into interstellar space at velocities high enough to break free from its star's gravitational embrace forever. And then began the long journey. Tens of thousands, perhaps millions of years travelling through the near vacuum between stars. No sunlight warming its surface, no gravitational tugs from nearby planets. just the slow tumble through interstellar space, occasionally passing through molecular clouds, occasionally experiencing the gentle push of galactic magnetic fields, but mostly just coasting through emptiness. The surface darkened as cosmic rays bombarded it, breaking down organic molecules, creating the radiation-processed crust we see today. Ice trapped near the surface would have sublimated slowly into the void from the feeble heat of starlight from distant suns. But the deep interior remained frozen, pristine, a time capsule preserving the chemical conditions of its formation billions of years ago, and then, by sheer chance, its trajectory intersected our solar system. The gravitational influence of our sun began to curve its path. It fell inward, accelerating as it approached, until finally it crossed the orbit of Neptune, then Uranus, then Saturn, then Jupiter, diving toward the inner solar system. And for the first time in eons, sunlight intense enough to matter began warming its surface. The awakening began. We detected it relatively late in this process. By the time Atlas telescopes in Hawaii spotted the fuzzy patch of light that would become known as 3I Atlas, the comet had already been warming for months, already begun outgassing, already developed the coma and tail that marked it as an active comet, rather than an inert asteroid. We missed the very earliest stages of its reactivation. We don't know what it looked like when the first ice began sublimating, when the first jets appeared, when the coma first started to form. That information is lost. We can only infer it from models and from comparisons to other comets, observed from their initial activation. But from the moment we detected it, we've been watching continuously, and what we've seen is an object in constant evolution. Not settling into a stable state, but continuously reorganizing, continuously responding to solar heating, continuously surprising us with new behaviors. The shifts we're documenting, the changes in jet configuration and thrust vectors, are chapters in an ongoing story of transformation. A frozen relic from another star system experiencing the warmth of our sun for the first and only time, and reacting in ways that reflect its unique composition and structure. Now here's where the story gets poignant in a way. This might be the end for 3I Atlas. Not necessarily in the sense of catastrophic fragmentation, though that remains possible, but in the sense of its existence as a pristine interstellar object. Even if it survives this passage intact, even if the structure holds together, and the comet emerges from the inner solar system without breaking apart, it will have been fundamentally altered by the experience. The heat will have penetrated deep into its interior. Volatile ices will have been lost. The internal structure will have been stressed and modified. It won't be the same object that entered our system, and when it leaves, when it escapes back into interstellar space on its new trajectory, it will be colder and darker and quieter than before. The activity will cease once solar heating fades, the jets will stop, the coma will dissipate, and 3I Atlas will return to the long frozen dormancy of interstellar travel, but now as a different object, modified by its brief encounter with our sun. In a sense, we're watching its transformation, its metamorphosis from one state to another. And that transformation is happening through these shifts, through these evolving jets and changing forces, through the ongoing response to conditions it hasn't experienced in billions of years. There's also a statistical question that looms over all of this. How common are objects like 3I Atlas? How many interstellar comets are wandering through the galaxy at any given moment? And what does the existence of such objects tell us about the frequency and nature of planet formation and system evolution around other stars? These aren't idle academic questions. They connect directly to our understanding of how common planetary systems are, how often they produce comet populations, how often those populations get disrupted and ejected into interstellar space. The current estimates, based on the detection rate of interstellar objects over the past few years, suggest that there are enormous numbers of these wanderers, billions, perhaps trillions of comet-sized objects drifting between the stars in our galaxy alone, each one ejected from its home system at some point in the past, each one carrying with it a sample of the chemistry and composition of a distant protoplanetary disk. The galaxy, from this perspective, is awash in debris from planet formation processes occurring around billions of different stars, and occasionally, very occasionally, one of these objects passes close enough to our sun that we can detect and study it. That realization has profound implications for our understanding of the galaxy's structure and evolution. It means that planetary systems are not isolated islands. They're connected by the debris they eject, by the comets and asteroids and planetesimals flung into interstellar space during their formation and evolution. There's a continuous exchange of material happening on galactic scales, a mixing process that operates over billions of years. Molecules synthesized in one stellar system might eventually end up in another system entirely, carried by objects like 3I Atlas. Organic compounds, amino acids, perhaps even more complex prebiotic chemistry, could be distributed through this mechanism. This connects to the panspermia hypothesis, the idea that life or its chemical precursors might be spread between star systems through natural processes rather than arising independently in each location. While that remains speculative and controversial, the existence of interstellar comets carrying organic-rich material makes the mechanism at least plausible. You don't need to invoke alien spacecraft or deliberate seeding. Nature itself provides a transport mechanism through the ejection and capture of cometary material. Whether that mechanism has actually distributed life or prebiotic chemistry across the galaxy is an open question. But the transport pathway exists. Now let's bring this back to the immediate situation with 3I Atlas and the latest shift. What makes this particular shift significant is not just that it happened, but when it happened in the comet's journey. We're now months past perihelion, the closest approach to the Sun. Solar heating is decreasing as the comet moves outward. Naively, you might expect activity to decline, jets to weaken, the non-gravitational forces to diminish as less energy is available to drive sublimation. Instead, we're seeing the opposite. Activity remains robust. New jets may be opening. The thrust magnitude is increasing rather than decreasing. This counterintuitive behavior tells us something important about the thermal structure of the nucleus. Heat doesn't propagate through cometary ice instantaneously. It takes time for warmth from the surface to work its way into the interior. The thermal wave deposited during perihelion passage is still penetrating inward, still reaching new ice reservoirs, still triggering sublimation at depths that were too cold during the actual close approach. This is called thermal lag, and it's a well-documented phenomenon in cometary science. What makes it notable in 3I Atlas is the magnitude and duration of the effect. The fact that major new activity is appearing months after perihelion suggests a nucleus with significant internal structure, with layers of ice at varying depths, with substantial thermal inertia that delays the response to solar heating. This is consistent with a relatively large, possibly porous nucleus. Not a solid block of ice, but something more like a loosely packed aggregate with voids and gaps that slow heat conduction. That structure, that architecture, affects everything about how the comet behaves. It determines how quickly it responds to heating, how much gas it can produce, how the jets evolve over time, and critically, how stable it is against fragmentation. A loosely packed rubble pile structure is in many ways fragile. There's minimal tensile strength holding it together. The components are bound mostly by weak gravity and van der Waals forces between grains, but paradoxically, that same loose structure can make the object more resilient against certain types of stress. When outgassing occurs, when pressure builds internally, a loosely packed structure can accommodate some of that pressure through compression and rearrangement of particles, rather than requiring the stress to be relieved through fracture. It's like the difference between a rigid solid that cracks under stress versus a granular material that can deform and flow. Whether 3I Atlas's structure tends more toward the rigid or the granular is one of the key unknowns, and that uncertainty propagates through all attempts to predict its future behavior. If it's relatively cohesive, if there's some strength holding the components together beyond just gravity, then it might withstand the current stresses and survive this passage intact. If it's barely bound, if it's essentially a gravitational aggregate with no real structural integrity, then the mounting activity might be enough to pull it apart. We won't know which scenario applies until we see how the story resolves, but here's something we can say with confidence. The data we're collecting now, during this period of enhanced activity and repeated shifts, is the most valuable data we'll ever get on this object. When 3I Atlas finally moves beyond the range where we can observe it effectively, when it fades into the distance and becomes too faint for detailed study, we'll be left with whatever measurements we managed to collect during its time in the inner solar system, and those measurements will define our understanding of this comet for decades, perhaps centuries to come. That's why the current monitoring campaign is so intense. That's why telescope time is being reallocated, why researchers are working overtime to process data as quickly as it arrives, why there's a sense of urgency in the community. This opportunity is finite and fleeting. Every observation that gets delayed, every night lost to weather, every instrument problem that prevents data collection, represents information lost forever. The universe is offering us a chance to study an interstellar comet up close, to watch it evolve in real time, to measure its properties with modern instruments. But the offer has an expiration date. Soon, very soon on astronomical timescales, 3i Atlas will be beyond our reach. The practical timeline looks something like this. Over the next few months, the comet will continue to be observable from Earth-based telescopes, though it will gradually fade as it moves farther from both the Sun and Earth. The quality of observations will decline as the signal-to-noise ratio decreases. By perhaps 6 months from now, it will be challenging to detect at all except with the largest telescopes. By a year from now, it will likely be effectively lost, too faint and too distant for meaningful study. That's the window we have. That's the time available to extract everything we can learn from this visitor. And that window is why each shift matters so much. Each reorganization of the jet structure, each adjustment to the trajectory, each unexpected behavior, these are all data points that constrain our models and test our understanding. When the comet finally fades from view, we'll compile all these observations into a comprehensive dataset. That dataset will include position measurements from hundreds of nights, images showing the evolution of the coma and tail, spectra revealing compositional changes over time, photometric data tracking brightness variations. It will be a complete biography of 3i Atlas's passage through our solar system, told through numbers and images and graphs. And then the real work begins. The work of interpretation, of synthesis, of figuring out what it all means. Research teams will develop detailed models attempting to reproduce the observed behavior. They'll test different assumptions about composition, structure, rotation state, trying to find parameter combinations that match the data. They'll write papers presenting their findings, arguing for particular interpretations, proposing future observations that could test key predictions. The scientific literature on 3i Atlas will grow over years, with each new paper adding refinements, corrections, alternative viewpoints. This is how astronomy works when dealing with unique or rare phenomena. You observe as intensively as possible during the brief window when observation is possible. Then you spend years analysing what you collected, extracting every bit of information, debating interpretations, gradually building consensus around the most likely explanations. Future students will study 3i Atlas in their coursework, learning about interstellar comets using this object as a primary example. And decades from now, when perhaps dozens or hundreds of interstellar comets have been catalogued and studied, 3i Atlas will be remembered as one of the first, one of the prototypes that taught us how these objects behave. But I don't want to get too far ahead of the story. We're still in the observation phase. The comet is still active, still evolving, still surprising us. And the latest shift, the one that prompted NASA's alert, reminds us that the story isn't over. We can't yet write the conclusion because we don't know what it is. Will 3i Atlas stabilize? Will it fragment? Will it do something we haven't anticipated? The only way to find out is to keep watching. And that's exactly what's happening. Right now, on this night, somewhere on Earth, a telescope is probably pointed at 3i Atlas. An observer is collecting photons that travelled from the Sun to the comet and then across millions of kilometres to Earth, capturing them with sensitive detectors, converting them into digital data. Tomorrow or the next day, that data will be processed, calibrated, analysed. It will be compared to previous observations, fit to orbital models, scrutinised for any signs of change. And if something significant appears, if the residuals show new patterns, if the images reveal new structures, another alert will go out. Another update will circulate through the community. Another adjustment will be made to our understanding. This is science in action, playing out in real time. Not the sanitized version presented in textbooks where everything is neat and settled, but the messy, uncertain, exciting version where you're making discoveries as you go, where each new observation might overturn yesterday's conclusions, where you're constantly revising your understanding in response to fresh data. It's chaotic and frustrating and exhilarating all at once. And it's exactly what drew most of the researchers involved into this field in the first place. The chance to discover, to learn, to be the first to see something no human has seen before. For the scientists tracking 3I Atlas, every new dataset brings that thrill. What will tonight's observations show? Has the jet configuration changed again? Is the comet brighter or dimmer than predicted? Are there any outburst events, sudden brightenings that might indicate explosive release of trapped gas? These questions drive the work, motivate the long hours, sustain the enthusiasm even when the data is ambiguous or contradictory. Because somewhere in that data is information. Somewhere in those measurements is a clue to understanding. You just have to look carefully enough, think hard enough, be creative enough in your analysis to extract it. And sometimes, despite all the sophisticated instruments and careful analysis, the most important insights come from simple observations, like noticing that the comet's position is consistently offset from predictions in a particular direction. That simple observation, that pattern in the residuals, was what first alerted researchers to the fact that non-gravitational forces were significant for this object. It wasn't a complex spectroscopic signature or a subtle photometric variation. It was just the comet being in the wrong place, persistently, systematically. And recognizing that pattern, understanding what it meant, led to deeper analysis of the outgassing behavior, which revealed the jet structures, which informed models of the nucleus properties, which ultimately connects to questions about composition and formation conditions in the comet's distant birthplace. That chain of inference, starting from a simple measurement discrepancy and ending with insights about another stellar system, exemplifies the power of careful observation and thoughtful analysis. Every piece of data matters, every measurement contributes, even null results, observations that show nothing unusual happened, are valuable because they constrain what's possible. The full story of 3I Atlas will ultimately be told through thousands of individual observations, each contributing a small piece to the larger picture. Now let's address something that often gets overlooked in discussions of active comets: the dust. We've talked extensively about the gas, about sublimation, and jets, and thrust vectors. But comets don't just release gas, they also release dust, solid particles entrained in the gas flow and carried away from the nucleus. And that dust has its own story to tell. The size distribution of dust particles, the rate at which dust is produced, the way dust reflects sunlight, all of these properties provide information about the nucleus and its evolution. For 3I Atlas, dust observations have revealed interesting patterns. The dust production rate, the amount of solid material being released per unit time, has varied significantly. Sometimes it correlates with overall activity levels, with dust production increasing when gas production increases, but not always. There have been periods where gas production remained relatively steady while dust production spiked, or vice versa. These decorrelations suggest that different processes might be responsible for releasing gas versus dust, or that the dust-to-gas ratio varies across different regions of the nucleus. The size distribution of dust particles also carries information. Smaller particles, micron-sized grains, are easily lifted by gas flow. Larger particles, millimeter-sized chunks, require more vigorous gas emission to loft them away from the surface. When we observe what sizes are present in the coma, we can infer something about the intensity of the outgassing. During periods of particularly strong activity, when jets are vigorously erupting, we see larger particles present in the coma. During quieter periods, the coma is dominated by finer dust. This variation provides another window into how the activity level changes over time. There's also the question of where the dust comes from. Is it excavated from beneath the surface by sublimating gas? Or is it part of the refractory crust that gets dislodged when underlying ice sublimates? Both processes probably contribute, but their relative importance might vary. Fresh jets breaking through the crust might initially release a lot of crustal material as they excavate their vents. Mature established jets might primarily release dust from deeper layers. The compositional and textural differences between these sources could potentially be detected spectroscopically if observations are detailed enough. For 3I Atlas, the dust dynamics add yet another layer of complexity to an already complex picture. Each shift in jet configuration, each new active region, potentially changes the dust production pattern. And those changes in dust production, in turn, affect how the comet looks in images, how bright it appears, how the coma shape evolves. Disentangling all these coupled effects, Separating gas behavior from dust behavior, understanding how both contribute to the overall activity, is a significant analytical challenge. But it's a challenge worth tackling because the full story of this comet includes both components. Let me also touch on something that hasn't been emphasized enough in public discussions but matters enormously to the researchers involved: the international collaboration aspect of this work. 3i Atlas is being observed by telescopes and teams around the world. Data is being shared across institutions and borders. Researchers in different time zones coordinate their efforts to ensure continuous coverage. When weather prevents observations from one location, observers at another longitude step in. When one team develops a new analysis technique, they share it with others who can apply it to their own data. This collaborative approach is increasingly common in modern astronomy, driven by the recognition that major questions require resources and expertise beyond what any single institution can provide. But it's still remarkable when you step back and think about it. Scientists from dozens of countries speaking different languages, working at different institutions with different priorities, all coming together around the shared goal of understanding this one object. National boundaries and geopolitical tensions fade into irrelevance when you're all staring at the same set of data, puzzling over the same anomalies, working toward the same understanding. That collaboration extends beyond just sharing data. It includes regular teleconferences where teams compare notes, discuss unexpected results, debate interpretations. It includes joint papers where authorship lists span multiple countries and institutions. It includes mentorship relationships where established researchers guide students and postdocs, regardless of where they're located. The 3i Atlas campaign has strengthened international connections within the cometary science community, building relationships that will persist long after this particular object has faded from view. There's also a generational dimension worth noting. Some of the senior scientists working on 3i Atlas have been studying comets for decades. They remember the Halley missions in the 1980s, the excitement when multiple spacecraft flew past that iconic comet and returned the first close-up images of a cometary nucleus. They've seen the field evolve from a data-poor discipline where every comet observation was precious, to the modern era where we routinely discover dozens of new comets per year and can study them in extraordinary detail. For these senior researchers, 3i Atlas represents something new, even in their long careers. The first chance to study an interstellar comet with truly modern instruments. Meanwhile, graduate students and early career researchers are cutting their teeth on 3i Atlas data. They're learning observational techniques, developing analysis skills, writing their first papers. For them, this comet might be a defining experience, the object that shapes their research interests and methodologies for years to come. Some of tomorrow's leading cometary scientists are being trained right now through their work on this visitor from another star, and they'll carry those experiences forward, applying lessons learned from 3i Atlas to future objects, future campaigns, future discoveries. This transmission of knowledge and expertise across generations is fundamental to how science progresses. Each generation builds on what previous generations learned, adding new observations, developing new techniques, asking new questions. The 3i Atlas dataset will be studied by researchers who aren't even born yet, who will bring fresh perspectives and novel analytical approaches to data collected today. That's the long-term impact of campaigns like this. The immediate scientific papers and discoveries are just the beginning. The real legacy unfolds over decades as the data gets revisited, reanalyzed, reinterpreted in light of new understanding. Now, with all this context, let's come back to the immediate question. What should we expect next from 3i Atlas? What's the most likely path forward given everything we know? The honest answer is that we're in a regime of genuine uncertainty. The comet could stabilize. The activity could gradually decline as it continues moving away from the Sun, as the thermal energy deposited during perihelion is radiated away. As the deep interior slowly cools, the jets might weaken, the thrust might diminish, the shifts might become less frequent. In a few months we might look back and say, this was just a phase of enhanced activity that passed without incident. Or the activity could continue escalating. New jets could keep opening as heat penetrates to new depths. The thrust magnitude could keep increasing as more surface area becomes active. The structural stresses could mount until something fails catastrophically. In that scenario, we might witness fragmentation within the next few months. Not a gentle process, but a dramatic breakup that scatters the nucleus into multiple pieces, each following a slightly different orbit, each continuing to outgoal and evolve on its own. There's also a middle ground. The comet might experience a significant outburst, a sudden intense release of gas and dust without actually fragmenting. These outburst events are common in comets and can be quite dramatic, briefly increasing brightness by factors of 10 or more. They occur when subsurface pockets of volatile ice suddenly breach to the surface, or when large chunks of crust are explosively dislodged. After an outburst, the comet often settles back to a lower activity state, having released the pent-up pressure. Whether 3I Atlas will experience such an event is unpredictable, but the ongoing activity and structural stress make it plausible. The point is, we genuinely don't know which of these paths the comet will follow, and that uncertainty is what makes continued observation so important. We're not just collecting data to confirm what we already expect, we're watching to see what actually happens, ready to adapt our understanding to whatever nature reveals. This is exploratory science in the truest sense. We're exploring an object we've never seen before, watching it do things we can't fully predict, learning as we go. And here's something that often gets lost in technical discussions. There's beauty in this uncertainty. There's something profound and humbling about confronting a phenomenon you don't fully understand, about recognizing the limits of your knowledge, about being forced to admit that the universe is more complex than your models. Modern science, with all its sophisticated instruments and powerful computers, can do remarkable things. We can detect gravitational waves from colliding black holes billions of light years away. We can image the event horizon of supermassive black holes. We can measure the properties of exoplanets orbiting other stars. But we still can't definitively predict whether a kilometre-sized chunk of ice and rock will stay intact or break apart over the next few months. Not because we lack technology or computational power, but because the problem is intrinsically difficult. Too many variables, too many unknowns, too much complexity packed into this small, dirty snowball tumbling through our solar system. That challenge, that difficulty, is part of what makes science compelling. If everything were easy, if we could predict every outcome with certainty, there'd be no discovery, no surprise, no sense of wonder when nature does something unexpected. 3I Atlas, with its repeated shifts and unpredictable behaviour, embodies that sense of wonder. It's a reminder that despite all our progress, despite all we've learned, the universe still holds mysteries. And some of those mysteries are right here, close enough to study, small enough to fit in a telescope's field of view, yet complex enough to defy complete understanding. That juxtaposition of proximity and mystery is what makes comets, especially interstellar comets, so captivating. So what comes next? More observations, more measurements, more analysis, more waiting to see what the comet does. The latest shift has been documented, incorporated into updated models, discussed in team meetings and email chains. The community is watching, ready to respond to whatever happens next. And when the next shift occurs, when the next surprise emerges from the data, we'll be ready to document it, to analyze it, to learn from it. Because that's the process, that's how understanding is built. Not through sudden revelation, but through patient accumulation of observations, through careful analysis, through willingness to revise conclusions when new data demands it. For anyone following this story, the message is simple. Stay tuned. 3I Atlas isn't done surprising us. The latest NASA alert won't be the last. More updates will come as the comet continues its journey, as its behaviour continues evolving, as we continue learning. And each update will add to the story, will refine our understanding, will bring us closer to knowing what this visitor from another star is, really made of and what its fate will be. Before we close, I want to emphasise something. What we're witnessing with 3I Atlas is historically significant. A century ago, we didn't even know other stars had planets. 50 years ago, we'd never seen a comet up close. 20 years ago, we'd never confirmed an interstellar object passing through our solar system. And now, we're watching an interstellar comet actively evolving, tracking its behaviour in real time, documenting how an icy body from another stellar system responds to our sun's warmth. That's extraordinary. That's the kind of opportunity that comes along perhaps once per generation. The data being collected now will be studied for decades. The lessons being learned will inform our understanding of comets, of planet formation, of the galaxy's structure for years to come. And everyone involved, from the observers collecting data to the analysts processing it, to the theorists building models to explain it, recognizes that they're part of something special, something that will be remembered and referenced long after the current players have moved on to other projects and other questions. So yes, 3i Atlas has shifted again. The jets have rotated, the trajectory has been nudged, the thrust vector has evolved, and all of this matters because it's revealing the interior dynamics of an object we'll never have another chance to study. This is our one opportunity to understand what an interstellar comet looks like up close, to watch it respond to solar heating, to document its evolution from awakening to eventual quiescence. And we're not wasting that opportunity. We're observing with everything we have, analysing with all the tools at our disposal, learning as fast as nature will teach us. The universe delivered this gift to our doorstep. A visitor from the stars, active and evolving, close enough to study in detail. Our job is to make the most of it while we can, and that's exactly what's happening. The shifts will continue, the observations will continue, the analysis will continue. The story will unfold one measurement at a time, one image at a time, one surprise at a time, and when it's finally over, when 3i Atlas has faded into the distance and moved beyond our reach, we'll have a complete record of its passage. A testament to what's possible when humans point their instruments at the sky and ask, what's out there, and how does it work, and most importantly, what can we learn? That curiosity, that drive to understand, that willingness to be surprised and amazed by what we find, that's what makes us human. That's what drives exploration and discovery, and 3i Atlas is giving us a masterclass in all of it. A cosmic visitor that refuses to be boring, that keeps challenging our understanding, that keeps revealing new complexity just when we think we've got it figured out. It's exactly the kind of object that makes science worth doing. Difficult, unpredictable, complex, mysterious, and ultimately profoundly educational about the universe we inhabit and our place within it. So drop your location and local time in the comments. Where are you watching this from? What time is it where you are? Because right now, at this very moment as you're reading this, as you're thinking about this comet from another star, somewhere on Earth a telescope is tracking it. Somewhere an astronomer is analysing fresh data. Somewhere our understanding is advancing, one photon at a time, one measurement at a time. We're all part of this moment, this era of exploration, this time when humanity is learning to study visitors from beyond our solar system. Hit subscribe and turn on notifications because this story isn't over. When the next shift happens, when the next surprise emerges, when 3i Atlas does something we didn't predict, you'll want to be among the first to know. Will it stabilise? Will it fragment? Will it do something completely unexpected? The only way to find out is to keep watching, and that's what we're all doing together. Watching, learning, marvelling at what the universe has brought to our doorstep. History is happening, science is advancing, and a comet from another star is teaching us lessons we couldn't have learned any other way. See you in the next update. The cosmos is speaking, and we're finally learning to listen.